Parthasarathi is a professor in the Department of Information Science and Technology, Anna University. Her area of specialization is computer architecture and networks. One of her special interests is Indian language technology systems. She is actively involved in research in all the areas and has over 50 publications to her credit. She has about 25 years of experience covering both industry and academics.
Welcome to the UGC lecture series in computer science. This is a series of lectures in computer networks. We have been looking at the network layer. Today's topic would be a look at the IP protocol in the network layer. So, let us look at the IP protocol, which is the internet protocol. So, just to have a quick orientation of where we are located in the entire TCP IP model, take a look at this picture. So, you have the IP protocol at the network layer in the TCP IP model, right, at the IP the network layer. So, this is kind of in between your transport layer and the link layer. At the network layer, we also have other protocols such as the ICMP and IGMP protocols. Now, in the transport layer, you have the TCP and the UDP protocol. Both of these basically will talk to the IP protocol, that is IP will carry packets of both TCP and UDP. Okay. The current version of is version 4. Of course, we are moving towards version 6. So, you have actually both version 4 and version 6 currently being used, but the most commonly used one is still version 4, which is specified in RFC 891. Now, looking at the entire IP with respect to all the other protocols, IP is normally called as the waist of the hourglass. That is, if you look at all the different protocols starting from the application layer to the physical layer, the IP protocol appears as if it is the waist of the hourglass of the internet protocol architecture. That is, you could have multiple higher layer protocols and multiple lower layer protocols, but there is only one basic protocol which takes care of data forwarding at the network layer. So it is like saying that you have a thin waist. So, the IP protocol is supposed to be the waist of this hourglass model. So, you can see that this looks like an hourglass, right. So, this is the waist of that hourglass model. So, that is how the protocol has been designed. So, coming to the IP protocol, you can also say that it is the highest layer protocol which is implemented at routers. That is, you can see what happens. Now, typically you have application protocols at the end systems. TCP protocol also exists only at the end systems. The IP protocol is the only one which kind of exists in a TCP IP network at the routers. Now, at the routers you do not have the higher layer protocol. So, we say that IP is the highest layer protocol that is implemented at the routers. So, typically we know how data flows, right. So, it starts off from the application through all these layers, through the data link here up to the IP. This is where the routing decisions are taken, then again through the next data link layer and so on until we come to the final destination. Now, coming to the service that is provided by IP, we say that IP provides minimal service in terms of the delivery of packets. So, it provides an unreliable, connectionless, but what is called as best effort service. It is also called datagram service. Now, this best effort service is something which is very important to understand. So, what do we mean by best effort service? IP just says, I do not provide you any guarantees, but I will make my best effort to make sure that the packet you have given to me reaches the destination. So, it does not provide reliability. So, we say it is an unreliable protocol, which means it does not make any attempt to recover from lost packets. That is one of the first things we need to know. Secondly, it is a connectionless protocol. So, each packet is handled independently. So, IP is not aware that packets between hosts may be sent in logical sequence. It treats every packet independently. Okay, that is the second thing. Third of course, our best effort model that we are talking about does not make any guarantees on the service. No throughput guarantee, no delay guarantee, but it says I will make my best effort to deliver the packet to the network. So, we will see how IP actually provides this best effort service. Now, in fact, it is because of this best effort model of IP that IP is considered to be a very robust protocol, and it has survived over all the new networks that have come about. In fact, there is a very nice saying which says that even if you have a network which is formed by having two matchboxes connected by means of a string, even over that network, even over that communication channel, you will be able to have IP to run. So, IP is considered to be so robust because of its best effort model. Let us just take a look at how that happens. Now, because of this unreliable, connectionless and best effort model, let us first look at what are the consequences that we have. Consequences are that the higher layer protocols have to deal with losses or with duplicate packets. Now, we will actually be seeing that the TCP protocol, which is running at the transport layer, does exactly this. It will deal with losses and with duplicate packets. Now, packets also may be delivered out of sequence. Now, this is also something which could be delivered, which is typically handled by the higher layer protocol. Coming to the IP service, it provides 3 different types of service: unicast, broadcast and multicast. Unicast we know is a one-to-one service, broadcast is one-to-all, multicast is one-to-several, one-to-many. Okay. So, unicast is something like this, broadcast to all of them, multicast to just a particular group. Okay. So, this is what we have. So, and the IP multicast also supports a many-to-many service, that is also something which is provided, and it also provides it, of course it uses the support of other protocols for doing this. You have something called the IGMP protocol or the multicast routing protocol, which are used for doing the multicast operation, but otherwise it supports unicast, broadcast and multi. Now, coming to the IP datagram, the format of the IP datagram. So, this is basically what we have in the IP datagram. You have a version field followed by a header length, then there is something called type of service kind of a field, and then you have the total length of the packet, identification which is something like a sequence number, a set of flags, a fragment offset field, a time to live field, a protocol field, a checksum field, followed by the source IP address, destination IP address, and then a few optional header information followed by the actual payload. Now, the size of the packet, the entire packet consists of a header plus the payload, and the header itself, if you look at, has a constant portion plus an optional portion. So, the size of the header, if you look at, you can see that each of these, the rows that we have here is 4 bytes, 32 bits, okay, and we have 5 such rows which form the standard part of the IP header. So, 5 into 4 bytes, 20 bytes is the minimum size of a header, and maximum size of a header could be up to 60 bytes, okay, basically because the header length field here will tell you how big the header can be. We use 4 bits over here, 4 bits to specify the header field. So, you can have 2 power 4 different such 4 byte fields specified. So, 60 bytes is the maximum length of the header. Now, the total length of the packet as a whole, that is including the header plus the data part, again you could have IP datagram sent which do not have any payload at all, just the header itself could be the packet that is being sent. So, which means the minimum size of a header 20 bytes would be the total, would be the minimum size of a packet itself, but the maximum size of a packet would be determined by the length field that we have here, the total length field here. The total length field here is a 16 bit field. So, 2 power 16 bytes, right, that is 64 kilobytes or 65,536 bytes. That is the maximum size you can have for an IP datagram. So, 20 bytes to 2 power 16, 64 kilobytes is the variation that you have for an IP datagram. Okay. Now, another question that is an interesting question that comes up when you have such an IP datagram being sent is, in what order are the bytes of an IP datagram transmitted? The answer is that the transmission is done row by row, and for each row you first transmit bits 0 to 7, then 8 to 15, 16 to 23 and 24 to 31. So, this is called the network byte order, which is actually the big endian byte order. Coming to the fields of the IP header, let us look at each of the fields in detail. You have the version field, that is the very first field that we have, which is a 4 bit field. Now, current version is 4, of course the next version will be 6. Now, in fact, now I should not say next version will be 6. We have both version 4 and 6, which indicates, which basically will tell you what kind of a packet it is. Then you have a header length field, which is a 4 bit field. Now, the packet format that we have looking at now is the packet format for a IP version 4 protocol, the V4 protocol. So, it is in the IP V4 protocol that you will have the header length following the version, which again is a 4 bit field, which specifies the length of the IP header in multiples of 4 bytes. Now, the reason we need to have this header length field is because you can have in IP we have a standard header of 20 bytes plus some optional header. So, if you have optional header, how much of optional header is there? That information is specified by this header length field. So, it tells you where the header ends and where the data begins. Coming to the next field, the DS/ECN field. This field was previously called as a type of service field, but the role of this field has been redefined multiple times, but it is still backwards compatible to the TOS interpretation. So, what DS/ECN basically provides is, tells you is whether differentiated service is being used or not, and if differentiated service is being used, this DS field here, the 6 bits here are used to specify the service level, okay. What kind of differentiated service level is being specified. And the ECN field, right, there are 2 bits that are used for this. This is used in case we want to provide explicit congestion notification, which again is used, which will be used by TCP for doing some congestion control. Again, this is just information that is specified. This is not there in the original IPv4 protocol, but it is something which has been, when the TOS field has been redefined, it has been redefined to carry this ECN information, which can be used by the TCP protocol. Again, remember that IP does not do any congestion control, so IP does not use this information, but it just serves as a carrier for that information. It just takes that carrier, it is just a placeholder for that information. Okay. The next field that we have is the identification field, the 16-bit field. Now, this is a unique identification of a datagram from a host, and this is incremented whenever a datagram is transmitted. Then there are some flags that we have. There are 3 bits, 3 flags which are used. Of course, the first bit is always a 0, it is really not used, and then you have 2 other flags here, one called a do not fragment flag and one called an MF bit or a more fragments bit. Now, we will take a look at where these are used. These are actually used in something called fragmentation. So, when we take a look at when and how fragmentation gets done, we will take a look at these fields. Similarly, then we have a time to live field. Now, this specifies the longest path before the datagram is dropped, a 1 byte field is used. Now, the role of TTL field, I think we have talked about TTL a number of times. This is basically to ensure that a packet is eventually dropped when a routing loop occurs. Due to some mistakes or some errors that can occur in a routing table in any of the routers, it is possible that a packet keeps going from one router to another router and keeps going round and round in the network without actually reaching the destination. Now, this is obviously wastage of both the network's resources, and you do not want to have such a packet there. So, the TTL field is normally used to identify such packets and drop them. So, typically what we do is at every hop you keep decrementing this TTL field. When the TTL field goes to 0, we drop the packet. Okay, that is what is the purpose of this TTL field. So, this is how the TTL is used. So, your sender sets the value say to 64, and each router decrements the value by 1. When the value reaches 0, the datagram is dropped. Eventually, essentially what we are saying is that 64 hops it is allowed to go through in the network. If it goes more than 64 hops, we will drop it. So, it also means that if the distance between your source to destination is more than 64 hops, in that case also that packet will be dropped. That is something to guard against, which is why the sender typically sets the value, okay, anticipating that this is the maximum number of hops before the destination would be reached. And the default value that is used on the internet is 64. The next field is a protocol field. Now, this is a 1 byte field which basically specifies the higher layer protocol, and this is used for demultiplexing to the higher layers. That is, when an IP packet is received, you need to know whether that packet needs to be sent to the UDP protocol, TCP protocol, or whether it needs to be sent to the ICMP protocol, IGMP protocol, or whichever protocol. So, you have different numbers here which identify which is the protocol to which the IP packet is to be delivered. So, that is the purpose of this protocol field. Then we have the header checksum, which is a 2 byte field. It is a simple 16-bit long checksum which is computed for the header of the datagram. Then we have the options field. The options, there are a number of interesting information specified in the options. You could have security restrictions specified over here, and we have something called a record route option which is available. Now, this allows each router that processes the packet to add its IP address to the header. So, the idea would be that when you reach the destination, you would have a complete record of the route that has been taken by this particular packet. Similarly, we have a timestamp field which again allows each router to add not only its IP address, but also the time at which it received that packet to the header. So, you can also get an idea of the time that it takes for the packet to go from the source to the destination. Then we have something called source routing. There are 2 options here, loose source routing and strict source routing. Here, the source can specify the complete route that is to be taken to the destination. That is, it specifies a list of routers that must be traversed. Loose source routing just basically gives you a list of routers, not necessarily that it has to go exactly in that order. Strict source routing would mean that it specifies exactly that list of routers which needs to be traversed in that particular order. Now, this is done when the source wants to have control over how the packets are sent, rather than allowing the routing protocol to determine how the packets will be sent. So, these are basically the important fields that we have in the IP header. In addition to this, of course, there is one padding field which is there at the end, which basically is there to ensure that the header ends on a 4 byte boundary. So, we will take a short break now and come back and continue with the details of the IP header. Welcome back after the break. We've been talking about the IP datagram format. So, a quick look at the IP datagram format before we proceed with more details on that. We have already taken a look at the version field, the header length field, the purpose of the DS ECN fields, the total length, of course we know the purpose of this field, identification, then there are some flags plus a fragment offset. This is something that we have not looked at so far. Time to live field, protocol field, header checksum, then of course we have the source IP address, destination IP address which specifies the address, the options which is followed by the payload. Now let us come to an understanding of why we really have to worry about this fragmentation and fragment offset and so on. Now that basically has to do with the maximum transmission unit as defined for any network. Now the MTU or the maximum transmission unit basically tells you how much of data can actually be carried on a particular link. That is, though we say that the maximum size of the IP datagram is 64 kilobytes, the data link layer protocol generally imposes a limit which is much smaller. Now why does that come about? Because look at what happens here. Suppose I have an Ethernet frame. Now Ethernet frame can have a maximum payload of only 1500 bytes. So an IP datagram which is encapsulated in an Ethernet frame obviously cannot be longer than 1500 bytes, because remember that IP protocol data will be carried in a data link frame, in a data link layer frame, and if I am using an Ethernet at the data link layer, the Ethernet data cannot be more than 1500 bytes. So naturally an IP datagram cannot carried on an Ethernet frame cannot be greater than 1500 bytes. So the limit on the maximum IP datagram size therefore is imposed by the data link protocol, and which we call as the maximum transmission unit. Okay, so this is what we have as the MTU. So in this case, for instance, we say MTU for the Ethernet frame is 1500 bytes. So for various data link protocols, this gives an idea of the MTUs that we have. Ethernet is 1500, 802.3 it's about 1492, 802.5 uses 4464 and so on. For PPP protocol, in fact it can be negotiated. So this is how the MTU varies. So now because we have this maximum transmission unit, sometimes there is a necessity that IP packets need to be fragmented so that they are able to fit into this data link layer frame. So we will look at how that happens. So what is this IP fragmentation that we are talking about? So the IP fragmentation is required whenever the IP datagram exceeds the MTU, right? So the question is, what if the size of an IP datagram exceeds the maximum transmission unit? So the IP datagram has to be fragmented into smaller units. So now the question is, what if the router contains networks with different MTUs? Okay, for instance, I have from host A to host B, I am going through first an FDDI network, right, which has an MTU of 4352 bytes. Then through a router it goes to another Ethernet network which has an MTU of 1500 bytes before it reaches host B. If you had just a single network between two hosts, then your IP layer, since it knows which is the data link layer on top of which it is running, can always just look at that the MTU of that and make sure that it only sends packets of that particular size. That is easy to do. But when you have two different networks or two or more networks, each with different MTUs, what is to be done? That is the question. Okay. So here what we do is fragmentation, that is the router which determines that a packet that it has cannot now be transmitted as such, will have to be split into smaller datagrams before it can be carried in the current network, will do this job of fragmentation. So we say that the IP router splits the datagram into several datagrams, and these fragments are reassembled at the receiver. So we talk about fragmentation and reassembly. So these are two important things which become necessary for an IP protocol to work correctly. So every router, intermediate router therefore, will have to do this job of fragmentation if necessary. So it should have the capability to do this fragmentation. So where exactly is fragmentation done? Answering that question, it can be done at the sender or at the intermediate routers. There is a sender itself may have to do the fragmentation, or it may have to be done at the intermediate routers. And the same datagram can be fragmented several times. Okay, and the reassembly of the original datagram is only done at the destination hosts. Now we can come up with an explanation as to why reassembly is done only at the host, at the destination host. Let us first take a look at the fragmentation first. Now fragmentation, as I said, can be done at the sender or at the intermediate routers. So look at what will happen now. I will have the IP datagram with its header, right, and when this is fragmented by a router, the same IP datagram will be sent as fragment 1 and fragment 2. Again this header, each of them will have a complete IP header, but the information on this IP header will identify these as fragments and also the sequence of the fragments. So we need to look at how that is done. So what is actually involved in fragmentation? The fields which help in IP fragmentation are these fields which are marked in red over here. The total length field, then you have the identification field, and then you have these two flags, the don't fragment bit and the more fragments bit, and a fragment offset field. Okay. So the identification field, which we said is something like a sequence number, is the same for all the fragments. So when a datagram is fragmented, the identification is the same in all fragments. So this field serves to identify that these different fragments belong to the same original packet. Okay, so that is an important information. Second, we have these flags, DF flag and the MF flag. Now DF flag is set if we do not want fragmentation to be carried out, and so if you come to a router where you cannot carry it further without the help of fragmentation, and if this DF flag is set, then all you will do is just discard that particular packet. Okay, just is discarded if the MTU is too small. Okay, but this MF flag is more important for us. This MF flag, this basically indicates that more fragments are to follow. Okay, so this datagram is part of a fragment and an additional fragment follows this one. This information is set by this, is given by this MF bit. So if MF bit is equal to 1, it indicates that more fragments are going to come. If MF bit is equal to 0, it indicates that this is the last fragment. So you also have indication of how many whether there are more fragments to follow and whether this is the last fragment. That is given by this MF bit. Now the fragment offset bit field, that is the one which allows you to order these fragments. So what fragment offset gives you is the offset of the payload of the current fragment in the original datagram. Okay, and the total length is the length of the current fragment. Okay, this is how the information is specified. I will take an example to see how exactly all this information is used. Okay, so I am considering a case where an IP datagram of 4096 bytes is being sent. Okay, let me assume that the Ethernet is sent over Ethernet where the MTU is 1500 bytes. Okay, so let us look at what happens here. Now the 4096 bytes of data has to be now split into multiple fragments. Now remember that each fragment cannot be greater than 1500 bytes. So if you look at the fragments that are actually there, we'll just take a look at this fragment and then we'll explain, I'll give you an explanation as to why it is so. So you have the Ethernet header will be there, which is followed by the IP packet as such. Okay, so you have the identification field which is N, which remains the same. Now the offset field here is 0, right, which for the first fragment the offset field is 0, then you have the rest of the header, and this carries 1480 bytes of data. Okay. Similarly, in the next field the more field will be set to 1, the identification number remains the same in the next fragment, and the offset value is set to 185, then the rest of the header is the same as it is, copied as it is from the original IP packet. Again 1480 bytes of data are carried here. 4096 bytes of data that we have, 1480 and 1480 have been carried in the first two fragments. So the remaining 1136 bytes of data is carried in the last fragment. This fragment has a same identification, but the more bit is set to a 0, and the offset field here indicates the further that this is further down in the entire packet. Okay. Now there is something that we need to remember to look at over here. Now we will look at this number that we use here. We are using 1480 bytes of data instead of 1500 bytes. We said that the MTU is 1500, but why is it that we have only 1480 bytes of data that is being carried here? That is because the 1500 is the size of the entire IP packet which can be carried. Remember that we have 20 bytes of the header as such, right? So 20 bytes of the header plus 1480 bytes of data is what is carried in the IP data. So the amount of data that is fragmented is 1480. So 1480 in the first fragment, 1440 in the second fragment, followed by whatever is remaining in the third fragment. Similarly, if you look at the offset field over here, again the offset should have specified a value of 1480 as the offset in the second fragment. The first fragment is starting with an offset of 0 because it starts exactly at the beginning of that first data of the packet. Now the second fragment consists of data starting from the 1480th byte. So, okay. So 1480th byte onwards is what is being carried over here. So the offset value here must have been 1480. Instead, we use a value of 185. Now why is this so? Again, this has to do with the number of bits that are actually allocated for the fragment offset field. We only have 13 bits allocated for the fragment offset field, which means that the fragment offset field measures the offsets always in chunks of 8 bytes. Okay? So you have 1480 divided by 8 as the offset that is to be specified. So that is why we have a value of 185 specified over there. Okay? So if we look at how the IP datagram is actually carried on two different networks. So let's take a look at this particular example again. This is another example now. The sender is sending 8000 bytes. Okay? This is going on a token ring network. And then you have a router which is sending it on an FDDI network. Then it goes to another router which is connected through an Ethernet network before it goes to the final destination. The routers remove the IP frame from the data link frame, whether it is token ring, FDDI and so on, and look at the IP address to determine where to forward the frame. If the outbound MTU size is less than the IP frame size, then the router fragments the IP frame before giving it to the data link layer. Okay? So let's look at what is actually happening over here. The TCP layer gives it to the IP layer, and then here you transmit it on the token ring. So this is, it comes on the token ring over here. So the router over here will determine whether it needs to do the fragmentation or not. Now if I have a higher sized IP packet here than what can be carried on this FDDI, you will fragment it. Now each of those FDDI fragments, if they are again larger than what can be carried on the Ethernet, each of them will again further be fragmented, and then it will finally reach the destination. Okay. So let's look at this example. So we have 8000 bytes of data that's being sent on the token ring network. Okay. So we have an original data, the IP is on the token ring, you have the IP header, identification value let's say is n, more flag is 0, offset is 0, and it carries 8000 bytes of data. This basically indicates that the entire packet is a single packet which has not been fragmented. Okay. Now at router 1 this is going to be fragmented because our FDDI has a maximum of only 4500 bytes. So 4480 bytes of data can be carried. So 8000 bytes that I have is split into two packets, one of 4480 bytes and another of 3520 bytes. The first one has an offset of 0, more flag is set to 1. Second has an offset of 560, more flag is set to 0. So you have two fragments coming to router 2. Look at what happens on router 2. Router 2, each of these now have to be further fragmented because this is running on an Ethernet network which can only carry 1480 bytes of data. So the 4480 bytes of data that I have, the first fragment is now further fragmented into one fragment of 1480, another fragment of 1480, another fragment of 1480, right, and then whatever is left out, right. So that will be the fragments that you have in of this first fragment. Then in the second fragment I have 3520, right. This 3520 again is split into 1480, 1480 and I am sorry 3480s and the remaining data, right, 560 bytes of data. Now the offset field will clearly indicate to you which is the order in which these fragments are being sent, and the more field again you can see this more flag bit, other than the last fragment all the others will have the more fragments set to 1. So now at the destination you will receive all these different fragments, and the destination is the one that is going to take care of reassembling these fragments. Now how does it reassemble them in the correct order? It knows from the MF field what is whether there are more fragments to follow or not. From the offset field it knows which is the order in which the packets have to be reassembled, and it knows the size of each of these packets, so it can just put them in order, right. So this is how the fragmentation works. So the reassembly part, as I said, takes place at the destination machine. Okay. So as we saw over here, okay, this is yet another example showing you the data being transferred on a Ethernet frame, Ethernet network followed by a PPP network which has a 532 byte MTU followed again by a 1500 byte MTU. Okay. So now what happens here is router 1 would have already fragmented it to become 532 byte frames, but router 2 actually has 1500 byte MTU on which it can send it. So the question that comes up here is, should router 2 reassemble the fragments? The answer is no, because we do not know whether there is going to be another router through which it has to be sent before any further fragmentation needs to be done. So, the reassembly is normally carried out only at the destination. Okay. So, it is the final destination which reassembles frames. The receiver normally uses a timer to decide when to discard incomplete frames, because it is possible that due to some error a particular fragment does not arrive at all, in which case you will not be able to reassemble it. So, the timer is usually set to about 30 seconds. But remember that this fragmentation and reassembly is an expensive process. So, fragmentation increases the overhead bits, and the receiver must allocate buffers for reassembly, but has no way of knowing how many fragments there actually will be, and the reassembly also takes up some time. And if any fragment is lost or damaged, then all the fragments must be discarded and retransmitted. But IP does this fragmentation and reassembly basically because it says I will provide a best effort service. Fragmentation reassembly is one major mechanism which allows IP to provide this best effort service, and remember I told you that IP can run on top of any network. It is able to do so basically because of this fragmentation and reassembly mechanism. So, what we have looked at today is the details of the IP protocol, which is basically a best effort service. We have looked at mechanism, the fragmentation and reassembly mechanism which basically allows this best effort service to take place, and we also looked at a look at the number of fields which are there in the IP header. We still need to take a look at the addressing and other mechanisms, which we will do in a subsequent lecture. A few questions for you to consolidate today's material. Why does IP provide only best effort service? Question number 2, what is the implication of best effort service? Question number 3, what is the minimum size of an IP packet? Question number 4, what is the maximum size of an IP packet? Question number 5, why does IP do fragmentation? 6, which are the fields that help in fragmentation and reassembly? 7, what is the purpose of the TTL field? 8, how big are IP addresses? These questions should help you to consolidate today's material. Thank you.